TOCTOU, time of check to time of use, is a race condition that strikes when a program checks a file's state, and then uses that file, trusting nothing changes in between. The check phase is where it all begins. A program inspects a file at a predictable path like /tmp/myapp.lock, verifying it exists, looks safe, and is ready to write. But the moment between check and use is a window of vulnerability. An attacker runs a loop in the background, constantly deleting the legitimate file, and replacing it with a symlink aimed at something sensitive like /etc/password or /root/.ssh/authorized_keys. All it takes is winning that millisecond race. The use phase is where the damage lands. The program confidently opens /tmp/myapp.lock, believing it is its own lock file, but the kernel follows the symlink and writes attacker-controlled data straight into a sensitive system file. The check passed. The file was different. The program never knew. Predictable file names are what make this attack possible. The moment a program uses a fixed name like /tmp/myapp.lock, an attacker can pre-create a symlink at that exact path pointing wherever they want, long before the vulnerable program ever runs. The fix is to eliminate the race window entirely. Use atomic operations like open, with O_crete and O_execl, which create the file in a single indivisible step, failing if it already exists. Combine that with unpredictable names, mktemp, mktemp, or random suffixes, and there is nothing for the attacker to swap or pre-plant. The /tmp directory is a shared scratch space where any user on the system can create files. That world-writable design makes it convenient, but it also opens the door to users clobbering each other's files unless another layer of protection kicks in. That protection is the sticky bit. On /tmp the mode is 1777. The leading one sets the sticky permission, shown as the letter T in the symbolic form drwxrwxrwt. With this flag, only the file's owner, the directory's owner, or root can delete or rename a file. Everyone else is locked out, even though they still have write access to the directory itself. But the sticky bit only guards deletion. It doesn't stop file name collisions. If your script writes to a predictable path like /tmp/myapp.lock, another process, or an attacker, can race you, create that file first and hijack your data. The fix is simple. Names must be unpredictable. That's exactly what mktemp solves. It generates a random suffix using secure randomness, then creates the file with O_execl semantics, meaning the kernel atomically fails the open call if the name already exists. You get a guaranteed unique path returned to your script, with no race window for anyone else to slip in. Mktemp comes in 3 useful flavors. Plain mktemp creates a file in the directory named by tempdir, defaulting to /tmp. Mktemp D creates a directory instead of a file, perfect for staging a workspace. And mktemp T followed by a prefix gives you a custom template, so the temp name carries your application's fingerprint for easier debugging. You can verify the sticky bit yourself in one of 2 ways. Run stat/tmp and look for mode 1777 in the output, or run ls, ld/tmp and read the mode string. The trailing T in drwxrwxrwt confirms the sticky bit is active. That little t is what keeps /tmp a safe shared space. Welcome. In the next few minutes we'll use mktemp to create safe temporary files and directories, then verify that /tmp is protected by the sticky bit. All examples run as a normal, unprivileged user on a standard Linux system. We start with clear. It wipes the visible scrollback, so our demo begins with a clean slate. Nothing fancy, it just resets the display so each command's output is easy to read. Now we run mktemp with no arguments. It creates a unique temporary file in /tmp and prints its path. The 3x characters get replaced with random characters to guarantee the file name won't collide with anything else. Adding D tells mktemp to create a temporary directory instead of a file. This is useful when you need a scratch workspace for several related files. The directory inherits the same secure naming guarantees. The T flag lets you provide a custom prefix, which makes the temp file easier to identify in a long listing. Here we prefix with myapp, so anyone scanning /tmp immediately knows which tool created the file. Now we inspect /tmp itself with lsld. The trailing T, where you'd normally expect an X, is the sticky bit. You can see it on the very last character of the permission string. The sticky bit means users can only delete files they own inside /tmp. To confirm the sticky bit in numeric form, we use stat with a format string. The mode 1777 decodes as 1 sticky, followed by the standard 777 permissions. That leading one is what prevents users from removing each other's files in /tmp.